Hey guys, this is Mr. Mitchell. Today we're going to be talking about mechanical waves. So first of all, what is a wave? Let's just go back and remember for a moment that a wave is a disturbance that carries energy through matter and space. And so it's carrying energy, not matter itself. Waves do not carry matter at all. The only thing that's traveling with the wave is energy. Right, so we have a picture down here where we see a water wave going by, and there's something in there that's floating. Okay, and so that thing that's floating is representing a piece of matter. And so as the wave goes by, you don't see that matter travel downstream or whatever with the wave. You just see the matter go up and then go back down. All right, and so the matter of the wave is moving, but it's not moving with the wave. And that's something that we always want to keep in mind when we're talking about waves. It's not moving the matter itself, it's the energy that's traveling with the wave. So what makes a mechanical wave different than just a regular old wave? All right, so there's going to be two major types of waves, mechanical and another type we'll talk about a little bit later, but for now we're just focusing on these mechanical ones. So what makes a mechanical wave unique is that it travels through physical matter, like we just looked at. All right, so it requires that there be some kind of physical object for the wave to come through. The material through which the wave travels is actually called the medium. Okay, so I have an example of a mechanical wave down here. It's a water wave that we're used to seeing in the ocean. All right, and the medium for that water wave is the water itself. It's the matter that the wave is traveling through, that the energy is traveling through. So that is what makes mechanical waves unique. All right, so there's two major types of mechanical waves. All right, those are transverse and longitudinal. I know it's big words, but we're going to look at each of those individually right now, just to kind of see what is the difference. So transverse wave is one where the particles of the medium move perpendicular to the motion of the wave. Now remember that perpendicular means that I have two things that are at a 90-degree angle. That's what perpendicular is. So I should have matter moving one direction, and I should have the wave moving the other direction, 90 degrees out of phase. So this is a small illustration of what a transverse wave might look like while it's moving. And so you see that there's particles that travel up and down, okay? And the actual wave itself is moving across, all right? And so that is that perpendicular motion we talked about. The particles move up and down, but the wave moves side to side, all right? And so that's what a transverse wave is. There's several parts to a transverse wave, and we've labeled a bunch of these already. We've talked about the amplitude in the past. The amplitude is the length from what this equilibrium line is here all the way up to the peak position of our transverse wave. Right, so that's what the amplitude is. And it could be also the distance from the equilibrium line down to the lowest part as well. Those are both considered amplitude. We also have what's called a crest. So we talked about that maximum position. A crest is the technical name we call for that top point of a transverse wave. And then a trough is the bottom part. Okay, and so that's kind of our technical jargon, our science jargon for those specific points. Now, wavelength is the distance between two of those parts, two parts that are the same. So either two troughs or two crests, that's called a wavelength, and we learned earlier that that's a cycle. So a wavelength is actually just measuring how wide a cycle is of this particular wave. So here's a couple examples of transverse waves that we've seen in everyday life. I'm going to save the guitar one because I think it's really cool. But this is just ripples in a pond. So you drop a little, water droplet into a pond, or you see rain falling, and then these ripples come out. And what happens is the water waves travel up and down, but you see the wave actually spread out. And so we see that perpendicular motion. The water moves up and down, and the wave goes side to side. Now this is an example of a transverse wave on a guitar string. And so what they did was they took a slow motion camera and they recorded the guitar while the guy was playing it. And then they kind of superimposed it all together, and you see exactly how the guitar string is creating sound. Right? And so you observed on there, right? Let me turn the sound off and I'll play it again. You observe on there that when he's plucking the strings, they're constantly moving. You see the wave travel down the string, but the string stays in the same spot. And so again, that's that perpendicular motion where we have kind of the transverse wave traveling through the string, and that's what creates the sound. So then we have longitudinal waves. We talked about transverse, we now have longitudinal. A longitudinal wave is one where the particles of the medium, they don't move perpendicular anymore, they're actually parallel to the motion of the wave. And so if the wave's moving side to side, the particles are moving side to side. So this is a small illustration of that. You see that as the wave travels down this way, right, the particles are going the same direction. So the parts of a longitudinal wave are not quite as many, all right? So we can identify a wavelength here, but it's between two parts that look the same, but they have different names this time. So the parts where we have kind of the particles all bunched up together are called compressions because we've compressed all the particles together. And then the parts where the particles get stretched out from each other is called a rarefaction. All right, and so anytime I go from a compression to a compression, that's a wavelength, or I go from a rarefaction to a rarefaction, that's another wavelength, just like in our transverse waves, just kind of special names for this one. Some examples of longitudinal waves, all right, we have just regular old sound waves, all right, so sound waves is actually when I speak, my voice compresses air molecules, and that wave travels through the air and reaches your ears, and you hear that. All right, and so sound waves are an example of a longitudinal wave. Another way that we can see this is on a slinky. All right, so if we stretch the slinky out and we kind of jockeyed it back and forth really quickly, we'd see the wave travel right through it like this. And so this is another example of a longitudinal wave, but more, more easy for us to see than maybe a sound wave. So that's the end of what we got for mechanical waves today. I hope this was helpful, and good luck on your Module 8 quiz.